Enrico Fermi, the architect of the atomic age, read and published by Mr. Books. Enrico Fermi stands as one of the preeminent figures in the annals of 20th century science, a scholar whose name eternally echoes amid the corridors of physics, mathematics, and the profound transformations that gave rise to the atomic age. This book, Enrico Fermi, the architect of the atomic age, undertakes a comprehensive journey through the pivotal chapters of Fermi's life and work, illuminating his indelible influence on scientific progress and the evolution of modern civilization. From the cobblestone streets of Rome to the tumultuous laboratories of wartime America, Fermi's voyage was marked by unparalleled intellectual prowess and a tireless quest for truth in nature's most enigmatic phenomena. Each chapter of this volume endeavors to portray not merely the brilliance of Fermi's scientific mind, but also the resilience and adaptability with which he navigated an era fraught with political upheaval and ethical quandaries. His contributions spanned the realms of quantum mechanics and statistical physics, as well as the pioneering experiments that unlocked the secrets of nuclear fission, ultimately shaping the destiny of nations and the course of world history. Fermi's childhood and early education in Italy laid the foundation for his extraordinary aptitude in physics and mathematics, a gift that would soon captivate renowned figures within Rome's scientific circle. The intellectual camaraderie that flourished among his peers fostered a robust scientific community, built upon a relentless pursuit of discovery and innovation. As Fermi's insights advanced the understanding of quantum theory and statistical mechanics, his experimental ingenuity propelled the study of neutrons, unveiling pathways to harness atomic energy that would redefine the limits of human achievement. Yet, beneath the luminous achievements, Fermi's life was shadowed by the complexities of living and working under fascist rule, contending against the tides of oppression and political strife. His resilience during these years epitomized the arduous balancing act faced by scientists whose knowledge bore both extraordinary promise and unfathomable risk. Embedded in this narrative is a reflection upon the transformative nature of science, the interplay between knowledge and power, and the enduring legacy of an architect whose designs continue to mold the present and future. As you journey through the chapters that follow, you will witness the unfolding of genius in the face of adversity, explore the depths of scientific revolution, and contemplate the profound ethical dilemmas born within the atomic age. May this exploration of Enrico Fermi's life and achievements inspire reflection and a deeper appreciation for the individuals and ideas that have sculpted our modern world. Chapter 1. A Child of Numbers, Early Life in Italy. Enrico Fermi's journey into the world of numbers and scientific inquiry began in an environment quietly conducive to intellectual development, yet marked by the modesty characteristic of early 20th century Italy. Born on September 29, 1901, in Rome, Fermi was the youngest of 3 children in a family that prized education, though none could have foreseen the prodigious talents their son would eventually manifest. Fermi's father, Alberto Fermi, worked as a chief inspector for the Ministry of Railways, while his mother, Ida de Gattis, presided over their household with an eye for discipline and precision. The Fermi family, modest in means but rich in encouragement, fostered a culture of curiosity and intellectual engagement in their home. Young Enrico's propensity for self-guided learning quickly distinguished him from his peers as he devoured books on mathematics, physics, and philosophy that most children his age struggled to comprehend. An early and profound influence in his life was his older brother Giulio. The two shared a bond both fraternal and intellectual, spending hours engrossed in puzzles, mathematical games, and scientific literature. Fermi's exposure to advanced concepts at a tender age forged a special affinity for patterns, numbers, and logic. Tragically, Giulio's untimely death at 16 left an irreparable void in Enrico's life, yet also served as a catalytic force, compelling him to pursue knowledge with renewed vigor and purpose. Fermi's scholastic path unfolded with precocity. He was self-taught in many fields, gleaning expertise from borrowed texts and public libraries, far ahead of conventional school curricula. His teachers, recognizing an extraordinary mind at work, gave him the freedom to proceed at his own accelerated pace. With keen analytic abilities and a capacity for abstract reasoning, Fermi quickly outstripped his classmates, mastering subjects that often perplexed seasoned instructors. Central to his development was his encounter with the book Elementrum Physicae Mathematicae by Adolfo Amadei, an engineer and family friend. The text captivated Fermi, encouraging experiments in physics and mechanics that he performed using improvised laboratory equipment at home. Amadei detected the spark of genius in Enrico and mentored him through complex topics, sparking an enduring passion for scientific exploration. Fermi's adolescence coincided with the backdrop of a transforming Italy, balancing ancient traditions with the burgeoning rise of scientific modernity. While the broader socio-political context remained largely unaware of the young prodigy, within Rome's academic circles, whispers began to circulate of a precocious boy whose understanding of theoretical and experimental science seemed timeless. Upon completing his secondary education, Fermi prepared for university entry with a level of preparation unique among his contemporaries. In 1918, he entered the prestigious Scuola Normale Superiore in Pisa, a place renowned for nurturing Italy's finest minds. The entrance examination, an intensive challenge in physics and mathematics, was not just a hurdle but an opportunity for Fermi to showcase his depth of knowledge and originality. He completed the task so brilliantly that faculty members immediately recognized his distinctive talent. His years in Pisa marked the transition from childhood curiosity to disciplined academic pursuit. Though still a student, Fermi spent countless hours conducting independent research, often venturing far beyond the official syllabi. His peers admired but seldom understood the full extent of his intellectual reach. As he delved into the writings of Newton, Maxwell, and other luminaries with scholarly devotion. Thus, in the formative years of his childhood and adolescence, Enrico Fermi laid the foundations for a life devoted to scientific advancement. Gifted with innate brilliance, fueled by familial encouragement, shaped by personal loss, and driven by an inexhaustible curiosity, Fermi emerged as a child of numbers whose trajectory would one day reshape the contours of physics and the destiny of an age. Chapter 2: Genius Revealed, Education and Mathematical Brilliance. Enrico Fermi's academic ascent at the Scuola Normale Superiore in Pisa embodied the convergence of innate genius and relentless discipline. This period marked not only his formal initiation into the world of higher learning, but also the awakening of mathematical and scientific brilliance that would define his legacy for generations. Fermi's entrance into Pisa was, in itself, a testament to his intellectual acumen. The entrance exam, designed to filter only the brightest minds, was handily surpassed by Fermi, whose solutions were so elegant and original that they caught the attention of faculty and peers alike. Quickly, he distinguished himself among the cohort as a thinker of rare quality, both meticulous and imaginative in his approach. The atmosphere in Pisa fostered competitive excellence, yet Fermi's orientation was less about rivalry and more about mastery. He immersed himself in the study of physics and mathematics, developing novel methodologies for problem solving, and engaging in profound theoretical explorations. His approach was characterized by simplicity and directness, often distilling complex phenomena into tractable core principles, a trait that would underscore his later work in both theoretical and experimental physics. Fermi's early academic papers, produced while still an undergraduate, revealed a capacity for innovation seldom seen among students. His investigations into electromagnetic theory, thermodynamics, and spectroscopy showcased a union of mathematical rigor with physical intuition. Even in the earliest stages, Fermi's work demonstrated a unique ability to bridge the abstraction of mathematics with the empiricism of experimental inquiry. Faculty mentors such as Luigi Puccionti recognized his prodigious gifts, offering him advanced opportunities and encouraging independent research beyond the confines of structured classroom learning. Fermi actively pursued correspondence with leading scientists, both within Italy and abroad. He sought the insights of physicists like Max Born and Wolfgang Ernst, establishing intellectual exchanges that expanded his scientific horizon. These dialogues introduced Fermi to emerging trends in quantum mechanics and atomic theory areas, where his own investigations would soon contribute groundbreaking advances. His university years were also marked by an affinity for teaching and collaborative learning. Fermi enjoyed explaining intricate theoretical concepts to colleagues and junior students, his clarity and patience earning universal admiration. This educational initiative foreshadowed his later role as a leader of the legendary Fermi Group, in Rome, a model for collaborative scientific culture that would influence generations of researchers. As Fermi matured academically, his interests broadened to embrace statistical mechanics and quantum theory, fields at the cutting edge of physics in the early 20th century. His first seminal publication, an analysis of quantum statistics, posited revolutionary ideas about the behavior of particles at atomic scales. This work, later known as Fermi-Dirac statistics, constructed an entirely new framework for understanding the properties of electrons, and laid the groundwork for the development of solid-state physics and quantum chemistry. Fermi's mathematical prowess was matched by a passion for experimentation. He devised laboratory apparatus and conducted precise measurements in spectral analysis and nuclear reactions, demonstrating both an intellectual and practical command of physics. Through these endeavors, Fermi honed a methodology that integrated theory with experimental synthesis that would come to characterize the best practices of 20th century science. The years spent in Pisa crystallized Fermi's intellectual identity, grounded in rigorous academic discipline, animated by imaginative reasoning, and guided by a spirit of inquiry. He left the university not only as a master of physics and mathematics, but also as an emerging visionary poised to change the field. Forever in the wake of his graduation, Fermi stood ready to shape the destiny of the scientific community. His formative years a prelude to the epical discoveries that were yet to come. Chapter 3: Rome's Golden Age of Physics. The migration of Enrico Fermi from Pisa to Rome marked the commencement of an era often described as the Golden Age of Physics within Italy. This period, beginning in the early 1920s and extending into the tumultuous 1930s, saw Fermi ascend to a position of pivotal influence, leading a new generation of physicists and revitalizing Rome as a center of scientific excellence. Upon his appointment as professor of theoretical physics at the University of Rome in 1927, Fermi inherited a relatively modest and under-resourced academic environment. Italian physics, though graced by notable historical figures, languished beneath the weight of tradition and isolation from the broader European scientific discourse. Fermi's arrival in Rome catalyzed a renaissance grounded in dynamism, innovation, and international engagement. Fermi's office quickly became a hub for intellectual exchange, attracting students, young researchers, and established scientists alike. His teaching style, characterized by clarity, rigor, and accessibility, enabled him to impart both the foundational elements and the subtle intricacies of emerging physical theories. Fermi's insistence on understanding physics from first principles oriented his students toward lasting insight and creative problem-solving. The community that coalesced around Fermi would later become known as the Fermi Group, a collaborative cohort distinguished by its egalitarian ethos and mutual respect. Notable among its members were Edoardo Amaldi, Franco Rossetti, Emilio Seeger, Bruno Pontecorvo, each of whom would go on to make significant contributions to physics. The group's interactions transcended hierarchical barriers, fostering an environment in which dialogue, debate, and cooperative experimentation flourished. Rome itself, during this epoch, was transformed through Fermi's leadership. He expanded laboratory facilities, advocated for modern equipment, and encouraged a regular influx of visiting foreign scholars. His efforts drew Italy into the vanguard of scientific research, bridging gaps with institutions in Germany, Britain, and the United States. Conferences, colloquia, and international workshops became routine features of Rome's intellectual landscape. Fermi's scientific productivity during these years was prodigious. He continued to refine his quantum statistics, publishing research that garnered international acclaim, Simultaneously, he advanced studies into beta decay and nuclear processes, laying the theoretical groundwork for understanding radioactivity and atomic transformations. The group's collective experimentation with neutron physics and nuclear reactions presaged historic achievements in the production and control of atomic energy. The ambience in Rome was both intense and inspiring. Fermi's approach to leadership drew out the best in every member, encouraging risk-taking and audacity in experimentation. The group's daily routine mingled rigorous scientific analysis with informal discussions, a blend that nurtured creativity and fostered a culture of resilient inquiry. Moreover, Fermi's presence elevated the prestige of Roman physics in national and international circles. Young scientists flocked to study under him, and the Italian government, recognizing the stature of his achievements, began to invest more substantially in scientific infrastructure. This golden age was not solely a product of intellectual brilliance, but also of visionary collaboration. The Fermi Group's distinctive blend of teamwork and innovation revitalized physics in Italy and exerted an enduring influence that would propel Italian science onto the global stage. In sum, the years in Rome not only supercharged Fermi's own development, but also ignited a broader revolution. Under his stewardship, Rome became a beacon of hope for aspiring scientists, a crucible for revolutionary ideas, and a testament to what can be achieved when genius is joined with collective endeavor. Chapter 4: The Fermi Group and a New Scientific Culture. The emergence of the Fermi Group in Rome signified more than just a congregation of brilliant individuals. It marked the genesis of a new scientific culture that would redefine how research, collaboration, and education were pursued in Italy and across the world. Enrico Fermi, by virtue of his intellectual stature and personal charisma, magnetized a select group of talented young physicists. Fermi's leadership style, rooted in humility, inclusivity, and a passion for discovery, established a framework that encouraged both independent thought and unified action. The result was an environment that transcended the traditional constraints of hierarchical academia. The group's daily life was characterized by rigorous discussion, joint problem-solving, and collaborative experimentation. Meetings often began informally, with members sharing ideas, presenting preliminary findings, and debating theories with animated enthusiasm. While Fermi presided as an unquestioned authority, his manner was never dictatorial. Instead, he stimulated participation on a dissent and cultivated a shared commitment to scientific excellence. At the heart of the Fermi Group's identity was its interdisciplinary nature. Members pursued research across diverse areas including spectroscopy, quantum mechanics, nuclear physics, and statistical theory, frequently merging insights from distinct fields to forge novel hypotheses and experimental designs. This multidisciplinary ethos distinguished the group from more traditional academic structures, which tended to privilege narrow specialization and rigid boundaries. Fermi's knack for nurturing talent was legendary. He identified strengths in his colleagues, assigning roles and responsibilities that matched their aptitudes and aspiration. Many members developed into leading figures beyond their association, with Fermi carrying forward his values of cooperation, creativity, and intellectual rigor. Central to the group's productivity was its commitment to both fundamental theory and practical experimentation. Fermi encouraged members to move fluidly between conceptual analysis and hands-on practice, believing that true understanding stemmed from the collision of mathematical reasoning and empirical verification. This approach yielded significant advances in fields ranging from neutron physics to nuclear transformations, culminating in discoveries that would pave the way for the peaceful and military applications of atomic energy. Outreach and communication formed another pillar of the group's culture. Fermi fostered connections with scientists internationally, inviting foreign researchers to visit Rome and sending group members abroad to study and collaborate. This openness to global dialogue enriched the group's perspective and enabled it to stay at the cutting edge of rapidly evolving scientific paradigms. The Fermi Group's style of collective learning and problem-solving began to influence scientific practice far beyond Italy. Visiting scholars marveled at the synergy of ideas, the generosity of mentorship, and the productive blending of theory and experiment that defined the group's identity. Ultimately, the Fermi Group embodied a new philosophy of scientific engagement, one that championed teamwork, cross-disciplinary insight, and fearless innovation. It left an enduring legacy not only in its discoveries, but also in the culture it created, inspiring generations of scientists to pursue knowledge collectively and courageously. As the world of physics changed in response to seismic scientific and political shifts, the Fermi Group remained a beacon of what could be accomplished through unity, vision, and mutual respect. Its influence survives today in the collaborative structures and values that underpin modern science. Chapter 5: Quantum Theory and Statistical Breakthroughs. The scientific milieu of the early 20th century was defined by upheaval, as new theories challenged the classical foundations of physics. In this context, Enrico Fermi emerged as a pioneer, particularly in the realms of quantum theory and statistical physics, fields that would come to redefine our understanding of nature at its most elemental level. Fermi's encounter with quantum theory began during his years at the Scuola Normale Superiore and was deepened through ongoing correspondence and collaboration with leading physicists across Europe. At a time when quantum mechanics was still nascent, its mathematical structure complex, and its physical interpretations hotly debated, Fermi's clarity of thought and intuitive grasp of fundamental principles allowed him to cut through the intricacies and make sense of the profound changes sweeping through physics. One of Fermi's most significant contributions was his development of what would later be called Fermi-Dirac statistics. In the early 1920s, classical statistics failed to adequately explain the behavior of certain types of particles, electrons, for instance, at atomic and subatomic scales. Building on the quantum postulate that some particles are indistinguishable, Fermi constructed a mathematical framework to describe how these particles, now known as fermions, behave according to the Pauli exclusion principle. His work established the foundation for much of quantum chemistry, condensed matter physics, and the eventual revolution in understanding electronic structure within atoms. Fermi's approach was characterized by a synthesis of rigorous mathematics and penetrating physical insight. He sought not only to explain observed phenomena, but also to anticipate new domains of inquiry. His papers were notable for their brevity, clarity, and remarkable predictive power, a style that influenced scientific communication for generations. Simultaneously, Fermi took a keen interest in statistical mechanics, exploring how the laws of thermodynamics intersected with atomic realities. He contributed original ideas to the study of entropy, energy distribution, and the behavior of gases at extremely low temperatures. Through both theoretical analysis and experimental verification, Fermi pushed the boundaries of what was known, challenging conventional models and proposing alternatives that would provoke new lines of research across physics. Perhaps most distinctive about Fermi's work was his ability to bridge theory and experiment. Many of his statistical models directly informed experimental design in spectroscopy, thermodynamics, and, notably, nuclear physics, a field that was just beginning to reveal its potential for transformative discovery. Fermi's quantum and statistical breakthroughs did not emerge from solitary contemplation alone. They were forged in collaboration and competition within a dynamic international community. Through publications, conferences, and direct exchanges with figures such as Paul Dirac, Wolfgang Pauli, and Werner Heisenberg, Fermi helped to shape the direction of modern physics, ensuring that Italy's scientific contributions would resonate across the world. The legacy of these breakthroughs is profound. Fermi-Dirac statistics remain central to physics, underpinning contemporary research in particle physics, superconductivity, and astrophysics. His work continues to inspire, a testament to the enduring power of clarity, rigor, and imaginative insight in the pursuit of knowledge. Chapter 6: Neutrons and the Path to Nuclear Physics. Enrico Fermi's foray into nuclear physics marked a turning point not only in his career, but also in the history of science. The discovery and subsequent study of the neutron particle first identified by James Chadwick in 1932, offered tantalizing possibilities for advancing the understanding of atomic structure and transformation. Fermi recognized, almost immediately, the immense potential inherent within neutron physics and set about leveraging this new tool to explore the heart of the atom. Up until the early 1930s, attempts to alter atomic nuclei had relied principally on the bombardment of atoms with charged particles, such as protons and alpha particles. These efforts were constrained by the electrostatic repulsion between the positively charged nucleus and the incoming particle barrier that made many reactions improbable or impossible. With existing technology, the neutron, being electrically neutral, could penetrate atomic nuclei more easily. Bypassing this problem and opening up new horizons in experimental physics, Fermi's approach was characterized by both audacity and methodological rigor. He reasoned that the neutron's unique properties might be used to induce nuclear reactions across a wide range of elements, leading a series of experiments in Rome. Fermi and his group began systematically bombarding different elements with neutrons, meticulously cataloging the resulting transformations. Their findings were breathtaking. Not only could neutrons provoke nuclear reactions heretofore impossible, but they could also generate new, previously unknown radioactive isotopes. One of Fermi's most notable achievements was the discovery that slow or moderated neutrons that had been slowed down by collision with light atoms, such as hydrogen in paraffin wax, were far more effective in inducing nuclear reactions than their fast counterparts. This insight arose from a series of brilliant empirical experiments, and it revolutionized the field. By harnessing the power of slow neutrons, Fermi paved the way for more controlled and efficient nuclear transformations. The implications of this breakthrough were immense. Contemporary scientists soon realized that the technique of neutron moderation could lead, in principle, to a chain reaction, a process in which a single neutron-induced event sets off a succession of reactions releasing extraordinary quantities of energy. This concept would lay the groundwork for both the development of nuclear power and the invention of atomic weaponry. Fermi's systematic studies yielded dozens of new artificial radioactive isotopes, expanding the periodic table and galvanizing research worldwide. His work attracted attention across Europe and America, prompting visits from leading figures and invitations to present his findings at international conferences. The pathway from neutrons to nuclear power, however, was not free from controversy or complexity. Fermi was acutely aware of the profound ethical and societal questions raised by the potential military and peaceful uses of atomic energy. These concerns would become even more pressing in the coming years as geopolitical tensions and the specter of war loomed ever larger. Nevertheless, Fermi's work with neutrons stands as a landmark in the trajectory of nuclear physics. His combination of theoretical ingenuity and experimental mastery unlocked the secrets of the atomic nucleus, inaugurated a new era in science, and positioned him as one of the central architects of the atomic age. Nuclear physics would never be the same with each experiment. Fermi deepened humanity's understanding of the universe's fundamental building blocks and set the stage for innovations that would change the course of history. Chapter 7: Discovering Slow Neutrons. The history of nuclear physics is built upon many foundations, yet few are so pivotal as the phenomena surrounding slow neutrons. Enrico Fermi's insight in this domain would prove to be one of the most transformative moments not only in his career, but in the trajectory of 20th century physics. In the early 1930s, the nucleus had already emerged as a subject of intrigue and speculation among physicists worldwide. Following James Chadwick's discovery of the neutron in 1932, scientists recognized the particle's potential role in facilitating nuclear reactions. Fermi's fascination began with the interaction of these newly found neutrons with various atomic nuclei, a pursuit that soon led him to challenge conventional wisdom. Traditional experimental setups made use of fast neutrons, typically generated via alpha particle bombardment. These particles, though powerful, often pass through matter with only limited interaction. Fermi and his colleagues at the University of Rome postulated that slowing neutrons might enhance their propensity for being captured by nuclei, thus enabling new forms of nuclear transformations. In a series of meticulous experiments, Fermi refined the art of neutron moderation by encasing radioactive beryllium sources in blocks of paraffin hydrogen-rich material. He observed a dramatic increase in induced radioactivity. The paraffin slowed the neutrons by repeated collisions with hydrogen atoms, transforming them from high velocity to slow or thermal neutrons. These moderated neutrons, by virtue of their reduced energy, could linger near atomic nuclei long enough to be absorbed, thereby triggering nuclear reactions previously considered improbable. The implications of this discovery were vast. Slow neutrons became the key to unlocking a universe of nuclear transmutations, enabling the synthesis of new elements and isotopes. Fermi's technique democratized experimental nuclear physics, allowing laboratories lacking sophisticated particle accelerators to conduct cutting-edge research with modest apparatus. Yet, beyond the practical, Fermi's slow neutrons revealed deeper truths about atomic structure and interaction. The enhanced likelihood of neutron capture suggested subtle complexities within the nucleus, encouraging the development of quantum models that would later shape the entire discipline. Fermi's work inspired a cascade of innovation around the world. Scientists in the United States, the United Kingdom, and the Soviet Union rapidly adopted and adapted his methods, pushing outward the boundaries of atomic theory. The ability to easily and reproducibly initiate nuclear reactions opened avenues, not only for academic inquiry, but for industrial and medical applications. Ranging from radioactive tracers to cancer treatments, the story of slow neutrons is inseparable from Fermi himself, a scientist whose intellectual agility and experimental dexterity defied the limits of orthodox thinking. His willingness to pursue novel paths, informed by rigorous observation and conceptual clarity, exemplified a spirit that would guide him through increasingly challenging scientific and political landscapes. As history would later reveal, the discovery of slow neutrons was not merely a technical advance, but the linchpin for humanity's entry into the atomic age. The principles Fermi uncovered would resound through the construction of nuclear reactors, the harnessing of atomic energy, and, ultimately, the forging of weapons whose destructive capacity would alter the fate of nations. In this chapter, we see Enrico Fermi poised at the threshold of greatness, wielding neutron science as both a key and a torch. His discoveries set in motion events that would transform science, society, and the future itself. Chapter 8: Science under Fascism, Italy in Turmoil. The ascent of fascism in Italy cast a long shadow across every facet of public life, including the realm of scientific inquiry. Enrico Fermi, by now recognized as one of Europe's finest physicists, found his career and conscience tested amid political turbulence, ideological oppression, and existential threat. Benito Mussolini's regime, openly hostile to democratic ideals and cosmopolitan intellectualism, increasingly sought to subordinate science to nationalist aims. Universities, traditionally bastions of free thought, were pressured to conform to state-sponsored orthodoxy. Scientists faced demands for ideological loyalty, and anti-Semitic laws modeled after those of Nazi Germany further poisoned the academic atmosphere. Fermi, whose wife Laura Capon was Jewish, understood the personal stakes of this new reality. Restrictions on public employment for Jews, censorship of scientific publications, and exclusion from professional societies rendered Italy's intellectual landscape hostile ground for innovation and collaboration. Many of Fermi's esteemed colleagues and friends, Edoardo Amoldi, Emilio Seeger, and Franco Rossetti among them, witnessed their research interrupted, their prospects darkened. Despite the climate of intimidation, Fermi strove to maintain the sanctity of his laboratory and the integrity of his work. His scientific output during the mid-1930s remained prolific. He continued pioneering research in nuclear physics, and his group earned international acclaim. It was during these years that Fermi was awarded the Nobel Prize in Physics 1938, a recognition not only of his technical mastery, but also of his resilience under duress. Nevertheless, the encroachment of fascist policy was inexorable. Scientific conferences were increasingly rare or tightly controlled. Foreign collaborations grew difficult, if not impossible. The regime's anti-intellectual thrust isolated Italian researchers from the global currents that animated physics, diminishing both the flow of ideas and the morale of the scientific community. Fermi, possessing a keen awareness of political trends and moral hazards, began to contemplate emigration. For him, the defense of reason, truth, and scholarly exchange outweighed allegiance to any nation or ideology. The Nobel Prize presented both validation and escape, offering the perfect opportunity for Fermi and his family to leave Italy. That they did so covertly, evading state scrutiny, testifies to the gravity of the situation. The broader effects of fascism on Italian science were stark. Laboratories languished. Innovative research slowed. Young scholars departed for foreign shores, further draining the country's intellectual capital. Through the lens of Fermi's experience, one perceives both the vulnerability and the resilience of the scientific enterprise, even as a regime sought to harness and manipulate knowledge for its own ends. Fermi stood for a higher fidelity to empirical truth, international fellowship, and the promise of discovery. His perseverance amid adversity remains a parable for all who cherish the independence of thought and the universality of human aspiration. This chapter serves as a chronicle of science amid suppression, elucidating not only the dangers of political overreach but the indomitable spirit of those who resist. In Enrico Fermi's journey, Italy's turmoil becomes the crucible of greatness, forging qualities that would animate his subsequent achievements on a global stage. Chapter 9: Exile and Opportunity, Journey to America. Enrico Fermi's decision to leave Italy was born of necessity, shaped by a quest for freedom, and buoyed by hope for new horizons. His journey, both literal and symbolic, ushered in a profound transformation, marking the passage from threatened scholar to transnational pioneer. The Nobel Prize ceremony in Stockholm served as the discreet departure point. Fermi, accompanied by his wife Laura and their children, departed Italy under the guise of an international celebration. Their exit marked the conclusion of a chapter spent negotiating scientific brilliance within an increasingly hostile environment, and the beginning of an odyssey that would redefine the very frontiers of physics. Upon arrival in the United States in early 1939, Fermi confronted both challenge and promise. The American scientific community, recognizing the magnitude of his achievements, welcomed him with open arms. Columbia University, already a nexus for nuclear research, offered him a professorship and the resources necessary to continue his investigations. Here, Fermi found both sanctuary and stimulation, poised to engage with a cadre of leading minds, including Leo Szilard and Isidore Isaac Rabi. Exile, though fraught with personal and professional adjustment, brought new opportunities. The United States operated under a culture of academic openness, benefiting from robust federal support and diverse talent. Fermi quickly acclimatized, leveraging a network of collaborators who shared his passion for discovery. The relative freedom from political restraint and censorship reanimated his creativity and ambition. Almost immediately, Fermi set about replicating and expanding his Italian experiments. He marshaled resources to construct apparatus for neutron moderation, performed innovative measurements of induced radioactivity, and initiated collaborations that would soon blossom into larger projects. The momentum was palpable. America was fast becoming the world's preeminent center for nuclear physics. Yet, Fermi's experience as an exile extended beyond the laboratory. He was acutely aware of the rising tensions in Europe, conscious that his work might soon acquire political and military dimensions. Conversations with peers, including émigrés fleeing Nazism, highlighted both the urgency of scientific progress and the moral challenges it entailed. Fermi's arrival amplified American capabilities. His methods, honed in Rome through necessity and ingenuity, proved adaptable and effective in the new context, and his analytical rigor set a standard for colleagues and students. As the world edged toward war, the question of nuclear fission loomed large. News from Europe, most notably Otto Hahn's demonstration of uranium fission, further supercharged the research agenda. Exile for Fermi was not merely a change of location but a reconfiguration of possibility. The journey from fascist Italy to the probabilistic, pluralistic landscape of the United States catalyzed a second act in his career, one suffused with both scientific optimism and ethical reflection. In this chapter, we trace Fermi's metamorphosis from the shadows of repression to the promise of innovation. His sojourn to America became entwined with world events, setting in motion discoveries that would reach every corner of the globe. The interplay of exile and opportunity, adversity and achievement renders Fermi's journey as both uniquely personal and universally resonant. Chapter 10: Columbia University and Nuclear Research. Upon settling at Columbia University in New York City, Enrico Fermi entered a vibrant intellectual ecosystem primed for a breakthrough. Columbia was quickly establishing itself as a focal point of nuclear research, drawing on the talents of established luminaries and enthusiastic newcomers alike. For Fermi, it was both a haven and a crucible, where tradition met ambition and urgent global events lent every experiment an edge of consequence. The campuses and laboratories pulsed with possibility. In the august halls of Pupin Physics Laboratories, Fermi collaborated closely with Leo Szilard, whose theoretical foresight complemented Fermi's empirical skill. Together, they began to devise more sophisticated apparatus for neutron detection and moderation, seeking ultimately to observe the chain reactions predicted by earlier European research. One of the principal problems at the time was the question of neutron absorption and multiplication. Could a sustained nuclear chain reaction be achieved within a controlled environment? Much of Fermi's work, building on his earlier discoveries, was dedicated to this pursuit. What was needed was a combination of materials: uranium as the source of fissionable atoms, and graphite or heavy water to slow neutrons. Precision in experimental design and data analysis was paramount, and Fermi's methodical style set the tone for the entire laboratory. Under his leadership, experiments were meticulously designed, reactors assembled, counters calibrated, measurements scrupulously recorded. Fermi's inclination to blend practical engineering with theoretical contemplation was a hallmark. The iterative process testing, refining, retesting became a template for the group's progress. Young physicists, exposed to this disciplined approach, rapidly adopted his methods, transforming Columbia into a model for collaborative scientific enterprise. Discoveries arrived nearly monthly. The team succeeded in producing measurable neutron multiplication using uranium and graphite. Fermi's calculations confirmed the possibility of sustaining a chain reaction, provided impurities in the graphite could be minimized, a subtlety often overlooked by others, but critical to the viability of nuclear reactors. Columbia also served as a fertile ground for cross-pollination. Visiting scholars brought insights from Europe. Industrial partners such as DuPont and Westinghouse contributed materials and technical expertise. The fusion of pure research and applied technology engendered a sense of urgency, especially as the specter of war loomed. By 1941, it was clear that nuclear fission, once a theoretical curiosity, had become a matter of national importance. Fermi's work at Columbia thus laid essential groundwork for what became the Manhattan Project. His group was among the first to demonstrate, on a laboratory scale, the physics upon which massive, energy-producing reactors could be built. Moreover, his pedagogical influence trained a generation of physicists who would go on to play leading roles in both civilian and military applications of nuclear power. This chapter charts the unfolding of scientific camaraderie, discovery, and rigorous inquiry at Columbia. Fermi's blend of modesty and exactitude, his openness to interdisciplinary collaboration, and his unwavering commitment to empirical truth made the university the epicenter of a revolution, whose effects remain indelible. Chapter 11: The Manhattan Project begins. With the United States' entry into World War II, the stakes of nuclear research shifted dramatically. Scientific inquiry became inseparable from strategic necessity, and Enrico Fermi found himself at the heart of a vast, Secretive undertaking, the Manhattan Project. The Manhattan Project represented the greatest concerted scientific effort in history to date, drawing together physicists, chemists, engineers, and military personnel in a race to unleash the power locked within atomic nuclei. The project's goals were multidimensional advance fundamental understanding, develop practical reactors and, above all, construct a weapon capable of deterring or defeating adversaries. Fermi's expertise and temperament quickly positioned him as a central figure. He was tasked not only with developing experimental reactors, but also with steering teams, authoring technical reports, and coordinating with other laboratories scattered across the country. The project's decentralized structure demanded both scientific authority and diplomatic skill. Fermi's understated style became an asset. Work proceeded under a veil of intense secrecy. At Columbia and, later, the University of Chicago, Fermi led efforts to design, construct, and optimize Pile's rudimentary nuclear reactors. These structures would allow scientists to observe the behavior of chain reactions in real time, providing indispensable data for refining both theory and engineering practice. The challenges were formidable. Materials were scarce, safety protocols evolving, and timelines compressed. Fermi's determination, resourcefulness, and collaborative spirit were essential in overcoming technical barriers. He stressed meticulousness and caution, cognizant of the risks inherent to pioneering new phenomena. Teams worked around the clock, balancing rapid prototyping with painstaking measurement. Under the auspices of the project, new facilities sprang up seemingly overnight: Oak Ridge, Hanford, and Los Alamos. Knowledge flowed through a labyrinth of controlled communication, with Fermi serving as both an advisor and an arbiter. His role was not simply managerial. He remained intimately engaged with experimental work, personally overseeing the assembly of piles, troubleshooting anomalies, and validating results. Interpersonal dynamics grew complex as military urgency collided with academic norms. Fermi navigated these tensions with characteristic patience and clarity. He instilled a culture of respect and integrity, mitigating competition and fostering shared purpose. His openness to diverse perspectives, chemists, mathematicians, engineers, facilitated a truly interdisciplinary effort. As wartime pressure intensified, the technical goals crystallized: design a reactor that could reliably produce plutonium, and develop a mechanism capable of initiating a controlled, self-sustaining chain reaction. Fermi's contributions here were decisive, both in technical ingenuity and in his ability to inspire and organize talent. The Manhattan Project's inception marked a historic pivot. Science, once an end in itself, became enmeshed with global destiny. Fermi's leadership, blending the rigor of a laboratory with the logistical demands of national security, propelled mankind to a threshold beyond which possibilities and responsibilities would multiply. This chapter unpacks the early Manhattan Project, revealing both the brilliance and the burden of collective action. Under conditions of existential urgency, Fermi's ability to harmonize vision, pragmatism, and discipline exemplified the qualities needed to transform atomic theory into a tangible reality. Chapter 12, Chicago Pile 1, the first controlled nuclear reaction. On December 2, 1942, beneath the stands of Stagg Field at the University of Chicago, Enrico Fermi oversaw one of history's most significant scientific achievements, the world's first self-sustaining, controlled nuclear chain reaction. The Chicago Pile 1 experiment encapsulated years of theory, months of engineering, and days of anxious anticipation. The team, handpicked and led by Fermi, comprised some of the most gifted physicists and engineers of the era. They worked in secrecy, combining uranium oxide, graphite blocks, and neutron detectors into a carefully calibrated lattice. Fermi's oversight was absolute. He personally reviewed every calculation, inspected every piece of equipment, and monitored every stage of construction. The technical objective was clear: demonstrate that arranging uranium and graphite in a specific geometry would allow neutrons to sustain a chain reaction, producing a controlled, measurable output. The reactor, rudimentary by today's standards, was immense: over 40 tons of graphite, Supporting 6 tons of uranium, all assembled by hand, safety considerations were paramount. The risks, while not fully understood, were formidable. The possibility of runaway reactions, toxic emissions, or catastrophic failure haunted every participant. Fermi's calm assuredness and analytic rigor provided reassurance. He devised Scram Systems emergency rods that could halt the reaction in case of unforeseen danger. The experimental run unfolded with deliberate precision. Step by step, Fermi directed the removal of control rods, tracking neutron multiplication with sensitive counters. As each rod was withdrawn, the reaction edged closer to criticality. At 3:25 p.m., Fermi announced, "The pile is self-sustaining. The reaction can be stopped and started at will." This understated declaration belied the epical nature of the achievement. The controlled reaction released only a fraction of a watt, trivial in raw energy, but monumental in implication. Fermi and his colleagues had proven that humanity could, through ingenuity and discipline, command the fundamental forces governing matter itself. The news was relayed to project leaders with a coded message. The Italian navigator has landed in the new world. It marked the birth of nuclear power, opening the door to both civilian energy programs and the production of wartime plutonium. In the months and years that followed, the principles demonstrated at Chicago Pile 1 informed the design of larger, more sophisticated reactors. Fermi's approach, meticulous, cautious, and empirically grounded, became the template for the field. The experiment's success spoke not only to technical mastery, but to the power of collaborative effort under inspired leadership. Chicago Pile 1's legacy remains profound. It demonstrated the feasibility of sustained nuclear energy, inaugurated a new era in science, and established a precedent for safety and transparency that endures. For Fermi, it was a personal vindication, a culmination of years spent probing the mysteries of the atom, and a testament to the enduring value of clarity, rigor, and resolve. This chapter traces the preparation, execution, and reverberations of Chicago Pile 1, situating Fermi's triumph at the intersection of possibility and responsibility. In commanding the atom, humanity was awakened to both promise and peril, a legacy that endures in every reactor and every debate over the future of energy. Chapter 13, The Quiet Leader. Fermi's scientific style. Enrico Fermi's reputation as one of the 20th century's greatest physicists is founded not only on the breadth and depth of his discoveries, but also on his distinctive approach to scientific inquiry and leadership. Although his name is now synonymous with innovation, his methods were subtle, his demeanor reserved, and his influence quietly pervasive. Fermi's scientific style was characterized by a rare combination of rigorous logic, experimental mastery, and humility, traits that set him apart from the more flamboyant personalities of his age. Born in Rome in 1901, Fermi's early education reflected his methodical nature. From the outset, he demonstrated an affinity for the mathematical and physical sciences, excelling in settings that prized precision and deep understanding. For Fermi, science was not simply the pursuit of answers, but a discipline of questioning, exploring, and refining uncertainties. His approach was profoundly collaborative. He believed that scientific progress depended upon the free exchange of ideas, even if he himself often spoke sparingly and listened intently. This quietude belied a fierce intellectual intensity. In the laboratory, Fermi's ability to bridge theory and experiment became legendary. Unlike many theoretical physicists who preferred chalkboards to apparatus, Fermi was equally adept at calculations and hands-on experimentation. His self-taught engineering skills enabled him to construct complicated instruments, assemble makeshift laboratories, and design new investigative procedures according to the challenges at hand. It was common for Fermi to lead by example, demonstrating solutions rather than merely prescribing them. Colleagues often remarked on his Fermi question approach, breaking down complex problems into manageable, quantifiable parts, instead of chasing after the unanswerable. Fermi posed questions that could be examined with clarity. His method was at once pragmatic and creative, yielding breakthroughs while also establishing standards for scientific rigor. The iconic Fermi problems, used today by students and professionals globally, attest to his legacy as a thinker who emphasized logical reasoning and realistic estimation over conjecture. Yet, it was Fermi's demeanor that truly distinguished him as a leader. Never one for self-aggrandizement, he maintained a modest profile, focused not on accolades but on the work itself. In group discussions, Fermi fostered environments of mutual respect, rarely dismissing ideas out of hand, and always encouraging the exploration of alternative hypotheses. His capacity to nurture young scientists and make complex concepts comprehensible became legendary, particularly in the international gathering of physicists during his professorship at the University of Rome and later at the University of Chicago. Fermi's scientific style was also shaped by the context of his times. The rapid evolution of quantum mechanics and nuclear physics demanded flexibility and adaptability. Yet Fermi managed to chart a course between tradition and innovation. Even when confronting radically new phenomena, he adhered to a balanced approach, melding intuition with disciplined analysis, speculation with measurement. This balance, combined with humility, did not prevent Fermi from making independent judgments. Throughout his career, he often challenged prevailing thought with new interpretations. His willingness to question authority and revise existing models contributed significantly to the evolution of physics, particularly in the domains of beta decay and quantum statistics. Ultimately, Fermi's quiet leadership established a model for scientific progress that resonates still. In a world where breakthroughs often come attached to bravado and drama, Fermi's quiet dedication, relentless curiosity, and unassuming mastery remind us that true greatness in science is as much about process as it is about results. His legacy endures not only in the theories and technologies that bear his name, but in the style of inquiry he championed, a style rooted in collective endeavor, thoughtful precision, and a quiet pursuit of understanding. Chapter 14. From Laboratory to Weapon. The arc of Enrico Fermi's career traces a path from the intellectual sanctuary of laboratories to the fraught landscape of weapons development, a transition that would shape the destiny not only of physics but of global affairs. This journey, marked by both scientific achievement and ethical complexity, began in earnest as the storm clouds of World War II gathered over Europe. Fermi's early research laid important groundwork for the transition from pure science to applied technology. By the late 1930s, his work on neutron bombardment and nuclear chain reactions had revealed the extraordinary potential of atomic energy. The realization that splitting the atom could unleash immense power precipitated a race among scientists, not simply for discovery, but for control over the fate of humanity itself. As fascism advanced in Italy and anti-Semitic edicts threatened his family, Fermi's personal circumstances forced a dramatic change. In 1938, after receiving the Nobel Prize in Physics for his work on induced radioactivity, Fermi emigrated to the United States with his wife, Laura, and their children. This relocation, motivated by both personal safety and professional ambition, placed Fermi at the heart of the American scientific community. Just as the implications of his research became gravely apparent, by 1942, Fermi's expertise had become indispensable. His appointment as a director in the Manhattan Project, the Allied effort to build an atomic bomb, marked a pivotal moment. In the covert laboratories at the University of Chicago, Fermi and his team constructed the first self-sustaining nuclear reactor, an extraordinary technical achievement heralded as the birth of the atomic age. The experiment, conducted beneath the squash courts of Stagg Field, demonstrated the feasibility of a controlled chain reaction, setting in motion a series of events that would culminate in the development of atomic weaponry. Though the transition from laboratory discoverer to weapons engineer was gradual, it was never wholly comfortable for Fermi. He wrestled with the implications of applying scientific knowledge to destructive ends, even as he understood the necessity of the Allied cause against tyranny. Within the Manhattan Project, Fermi often advocated for careful, measured progress, emphasizing safety, accuracy, and the broader ramifications of their work. Fermi's contributions spanned theoretical calculations, experimental designs, and logistical oversight. His collaborative spirit fostered a sense of cohesion among a diverse team of physicists, chemists, and engineers. Yet, the intensity of the wartime effort created an atmosphere in which moral considerations were frank and life subordinated to urgency. The knowledge that their research would soon be harnessed for war left an indelible impression on all involved. Aside from the technical challenges, Fermi faced the complexities of scale and secrecy. The Manhattan Project required a reimagining of laboratory procedures, the management of large groups, and the rapid development of new machinery. Fermi's facility with both theoretical and practical aspects proved invaluable, particularly in resolving crises and maintaining morale. By 1945, the transformation was complete. The atomic bombs produced at Los Alamos, using principles Fermi himself had elucidated, were dropped on Hiroshima and Nagasaki, altering the world irreversibly. The sequence of events leading from laboratory bench to battlefield laid bare the tension between scientific advancement and ethical responsibility. For Fermi, the transition was not only professional but existential. The realization that his work, intended to illuminate the mysteries of nature, had contributed to unprecedented devastation weighed heavily upon him. In post-war reflections, Fermi continued to wrestle with these questions, advocating for international control and ethical oversight. The journey from laboratory to weapon is a testament to the power and peril of scientific knowledge. It illuminates the profound responsibilities borne by those who create and deploy the tools of modern civilization. Fermi's navigation of this terrain stands as both a warning and an inspiration, a reminder that the pursuit of understanding carries obligations that reach far beyond the confines of the laboratory. Chapter 15: Hiroshima, Nagasaki, and Moral Reckoning. With the culmination of the Manhattan Project, Enrico Fermi and his colleagues witnessed the transformation of their theoretical constructs into instruments of war. The events of August 1945, when atomic bombs were dropped on Hiroshima and Nagasaki, forced a reckoning, one that would reverberate throughout the scientific community and beyond. The decision to deploy these weapons was the result of a complex interplay of politics, strategy, and urgency, but it was also fundamentally rooted in the work of scientists like Fermi. The magnitude of destruction wrought upon these cities, the instantaneous loss of life, and the lingering shadows of radiation marked a new epoch in human history, one where the boundaries between science, morality, and policy became inextricably intertwined. Fermi's reaction to the bombings was deeply nuanced. On one hand, he understood the military rationale, desire to end a brutal conflict and to prevent further loss of allied lives. The atomic bombs, in the eyes of the policymakers, were the instruments of decisive victory. On the other hand, Fermi was acutely aware of the profound ethical dilemmas, the civilian casualties, the long-term effects of radiation, and the demonstration of a power capable of annihilating entire societies. The moral inquiries that followed were immediate and intense. Within days, scientists who had contributed to the Manhattan Project began circulating petitions, debating the future of nuclear weapons and questioning their own roles in the horrors unleashed. Fermi, while not as outwardly vocal as some of his peers, participated in these dialogues with his characteristic thoughtfulness, balancing his sense of responsibility with the wider context of war and peace. One aspect of Fermi's response was his advocacy for transparency and international control. He understood that secrecy and unilateral action would only breed further distrust and competition. In meetings and correspondence, Fermi emphasized the need for open scientific communication, the establishment of oversight mechanisms, and the prevention of nuclear proliferation. He saw that the fate of the atomic age was not merely a question of security, but one of ethics and stewardship. Moreover, Fermi grappled personally with the implications of his discoveries. While he believed in the right of nations to defend themselves, he questioned the wisdom of unleashing such irreversible forces. His reflections on the bombings and their aftermath contributed to a body of scientific literature that sought to reconcile the pursuit of knowledge with the moral imperatives of humanity. The impact of Hiroshima and Nagasaki transcended the immediate devastation. It altered the perception of science itself. No longer simply a tool for progress, physics became a battleground for competing visions of civilization. Fermi's legacy in this context is as a figure both complicit and questioning, advancing technology while urging caution and collective responsibility. In the years that followed, Fermi joined others in advocating for peaceful uses of nuclear energy, encouraging the development of reactors for electricity generation, medical applications, and research. His efforts contributed to the shift in scientific priorities from weaponization to constructive engagement, a journey that would echo throughout the Cold War and into the 21st century. The moral reckoning initiated by Hiroshima and Nagasaki remains unresolved. The questions posed by Fermi and his contemporaries persist. What are the boundaries of scientific responsibility? How can the fruits of discovery be used to enhance rather than threaten life? The answers lie not in easy certainties, but in the ongoing dialogue between knowledge, conscience, and the inexorable march of progress. For Fermi, this reckoning was both personal and professional, an enduring legacy that shaped his subsequent work and defined his place within the turbulent landscape of the atomic age. Chapter 16: Building the Atomic Age. Enrico Fermi's contributions to the construction of the atomic age extend far beyond the development of weapons. His vision encompassed a future in which the mastery of nuclear processes would revolutionize energy, medicine, and industry, transformations that would reshape the contours of modern society. The initial breakthrough, the successful creation of a self-sustaining nuclear chain reaction, was achieved in December 1942 under Fermi's careful supervision at the University of Chicago. This experiment, referred to as Chicago Pile 1, represented more than a technical achievement. It was the foundational act of the atomic era. Fermi's design balanced theoretical elegance with practical effectiveness, using graphite blocks and uranium to generate controlled power. The careful calibration of quantities and geometries showcased Fermi's ability to blend mathematics, engineering, and intuition. The success of Chicago Pile 1 paved the way for further research and development. Fermi's team rapidly expanded upon these results, constructing larger and more efficient reactors capable of producing plutonium and, later, harnessing energy for peaceful applications. The scale of these efforts required new organizational frameworks, interdisciplinary collaboration, and unprecedented investment. Fermi excelled in these environments, guiding teams through complex problem-solving and resource management. Fermi's influence extended to reactor design, safety protocols, and the training of new generations of engineers and physicists. He collaborated with leading industrialists, policymakers, and academic institutions to refine the basic principles of nuclear technology, ensuring that the transition from laboratory concept to industrial-scale application proceeded with rigor and care. In the post-war years, Fermi advocated strongly for the peaceful use of atomic energy. He believed that the power released from the nucleus could be tamed for the benefit of humanity, providing reliable electricity, novel medical treatments, and solutions to resource scarcity. His optimism was tempered by realism, as he continued to warn against the misuse and dangers of nuclear technology. Fermi remained deeply involved in the debates surrounding reactor safety, waste disposal, and non-proliferation. His technical expertise and forthrightness made him a trusted advisor to government agencies and international organizations. He contributed to the foundational policies that would govern the uses of atomic energy, emphasizing transparency, collaboration, and risk management. The architecture of the atomic age, as envisioned by Fermi, was not merely technological, it was social and ethical. He understood that the application of nuclear science had the power to enhance or undermine the fabric of civilization, depending on the choices made by leaders and citizens. Fermi's insistence on education, oversight, and the responsible stewardship of resources remains a central pillar of modern nuclear policy. The legacy of Fermi's efforts can be seen in the proliferation of nuclear reactors for power generation, the development of radiotherapy for cancer treatment, and the ongoing exploration of fundamental particles and forces. His holistic vision, combined with technical excellence and a sense of responsibility, established a roadmap for subsequent generations. In summary, Fermi's role in building the atomic age was multifaceted and profound. He provided the scientific foundation, shaped technological innovation, and articulated the moral imperatives that continue to guide the application of nuclear science. His story is an enduring reminder that the structures of the atomic era require not only skillful engineers, but wise architects, those who understand the intricate balance between progress and prudence. Chapter 17, Teacher of Giants, Mentorship and Influence. One of Enrico Fermi's most significant yet understated contributions to the scientific world was his role as a mentor, a teacher of giants whose influence radiated across generations. His legacy as an educator is embedded not only in his direct instruction, but in the intellectual culture he fostered, shaping scientists whose work would expand the boundaries of knowledge. Fermi's teaching style was a reflection of his broader scientific approach, clear, concise, and deeply engaging. Unlike some professors who relied on elaborate lectures or demonstrative flair, Fermi emphasized the fundamentals, guiding students through complex subjects by grounding them in first principles. His courses on quantum mechanics, statistical physics, and nuclear phenomena became legendary for their accessibility and rigor. Perhaps more than any formal curriculum, Fermi's mentorship occurred in informal settings, small seminars, laboratory discussions, and collaborative problem-solving sessions. He was known for his openness to questions, encouraging curiosity and independent thought. The atmosphere around Fermi was one of intellectual egalitarianism. All students were invited to participate, debate, and explore, regardless of seniority or status. The impact of this approach was profound. Fermi taught not only the mechanics of physics, but the spirit of inquiry itself. Many of his students, dubbed the Fermi Group, would go on to make monumental contributions in fields as diverse as particle physics, astrophysics, and engineering. Figures like Emilio Seeger, Owen Chamberlain, and Chen-Ning Yang later, Nobel laureates, often credited Fermi with providing both the inspiration and the tools required for their success. Fermi's mentorship extended beyond technical instruction to the cultivation of scientific character. He emphasized honesty, perseverance, and humility, modeling these virtues in his own work. Errors, he taught, were learning opportunities, not sources of shame. His constructive feedback was delivered with kindness, fostering resilience and self-confidence among his protégés. He also recognized the importance of diversity in thought and background. Fermi championed inclusion, welcoming international students and collaborating with colleagues from varied traditions and disciplines. His cosmopolitan perspective created a laboratory environment that transcended national boundaries, enhancing the dynamism and creativity of the scientific enterprise. The personal connections Fermi formed with his students enriched both his teaching and their development. He often spent hours conversing with young scientists about their research, ambitions, and philosophies. These conversations extended Fermi's influence beyond the specifics of physics to broader questions of ethics, society, and the responsibilities of scientific citizenship. In summary, Fermi's role as a teacher and mentor was as impactful as his discoveries. Through his dedication to education, his fostering of independent inquiry, and his advocacy for scientific integrity, he shaped not just minds but cultures. The legacy of the giants he taught, each carrying forward his example of excellence and humility, remains one of the enduring pillars of 20th century science. Chapter 18, Fermi Beyond the Bomb, Post-War Physics. Following the cataclysmic events of World War II and the dawn of the atomic age, Enrico Fermi redirected his energies toward the pursuit of pure science, becoming a central figure in post-war physics. This period marked a transition not simply like scientific inquiry, but in its aspiration Fermi sought to illuminate the fundamental laws of nature, extending the reach of physics beyond the confines of military technology. Fermi's post-war research focused predominantly on particle physics, quantum theory, and cosmology. Having demonstrated the power and peril of nuclear energy, he now turned his attention to the more arcane facets of atomic and subatomic behavior. His work on mesons, neutrinos, and cosmic rays expanded the theoretical and experimental horizons of physics, laying the groundwork for later discoveries in particle accelerators and high-energy physics. In Chicago, and later at Los Alamos, Fermi led teams investigating the nature of weak interactions, the statistical behavior of particles, and the characteristics of newly discovered entities. His foundational theories, such as Fermi's theory of beta decay, proved central to the development of quantum, electrodynamics, and the eventual unification of the weak and electromagnetic forces. Fermi's post-war work also exemplified his capacity for innovation amid changing circumstances. The transition from wartime urgency to peacetime exploration required new funding models, organizational structures, and collaborative networks. Fermi proved adept at navigating these changes, securing resources, training young scientists, and establishing laboratories equipped for cutting-edge investigation. His technical contributions were matched by his philosophical engagements. Fermi advocated for the autonomy of scientific inquiry, resisting attempts by governments to dictate research priorities or restrict access to information. He argued that the pursuit of knowledge should be guided not merely by immediate utility, but by curiosity and imagination, a stance that reinvigorated the culture of open exchange. Fermi also remained active internationally, advising on the establishment of research centers, participating in global conferences, and promoting transnational cooperation. His reputation attracted scholars from across the world, transforming his laboratories into crucibles of innovation. Significantly, Fermi's post-war work suggested a vision of science as a force for unity and enlightenment. Where the bomb had divided humanity, the discoveries of physics offered opportunities for collective advancement. His continuing support for peaceful nuclear applications, his contributions to medical physics, and his engagement with educational reform exemplified the responsibilities of science in a changed world. Fermi's post-war legacy is thus one of transformation. He redirected the energies of a generation toward creative, constructive pursuits, redefining the goals and methods of modern physics. Through both theoretical insight and practical leadership, he reaffirmed the enduring power of inquiry, even in a world marked by uncertainty and risk. Chapter 19: Legacy in Science, Energy, and Ethics. Enrico Fermi's legacy reverberates throughout the tapestry of modern science, manifesting in enduring advances that straddle theoretical physics, practical applications in energy production, and a complex ethical terrain of atomic innovation. To appreciate Fermi's standing as a colossus in the scientific community, one must consider the scope and depth of his contributions, the transformative effects of his discoveries, and the profound moral considerations entwined with his work. From the outset of his career, Fermi distinguished himself as a prodigy in a country striving to find its place in the modern scientific world. Born in 1901, he entered the academic realm of physics at a time when the discipline was undergoing foundational change. The prevailing understanding of the atom, matter, and energy was in flux, as quantum mechanics began to unravel the mysteries of nature's building blocks. Against this dynamic backdrop, Fermi's intellectual curiosity flourished, driven by an unyielding determination to clarify the intricacies of the universe. Fermi's early forays into quantum theory and statistical mechanics established his reputation as an innovative thinker. His formulation of Fermi-Dirac statistics, which described the behavior of subatomic particles known as fermions, provided the theoretical underpinnings for much of modern electronics and condensed matter physics. This achievement, remarkable in itself, only scratched the surface of Fermi's scientific endeavors. His pioneering work in nuclear physics cemented his status as a trailblazer. The successful demonstration of the first controlled nuclear chain reaction in 1942 under the bleachers of Stagg Field at the University of Chicago was both a triumph of human ingenuity and a moment of profound ethical consequence. This feat launched the atomic age, enabling the development of nuclear power, which promised unprecedented energy resources while inseparably linking Fermi's legacy to the specter of nuclear weapons. Fermi's vision of peaceful atomic energy applications coexisted uneasily with the reality of atomic warfare. His advisory role in the Manhattan Project, which resulted in the creation of the first atomic bombs, placed him at the crossroads of scientific progress and moral quandary. Fermi wrestled with these complexities, recognizing that knowledge itself is neutral, but its uses can fashion destinies of liberation or devastation. Beyond the laboratory, Fermi's influence radiated through his mentorship of future Nobel laureates and his leadership in establishing norms for scientific collaboration and inquiry. His humility and didactic prowess fostered an environment in which questioning was encouraged, and rigor became the bedrock of discovery. His approach helped usher physics into an era of unparalleled productivity, where collective efforts produced advances that continue to shape technology, medicine, and our understanding of the universe. Nevertheless, Fermi's legacy is intrinsically bound to a set of moral responsibilities. The tension between innovation and its applications, particularly when discoveries bear on the survival of humanity, forces scientists and society alike to ponder the limits of progress. Fermi's life and career underscore the imperative of ethical reflection in the pursuit of knowledge, a theme that remains urgent as the power of science continues to expand. In conclusion, Enrico Fermi's legacy is not solely measured in Nobel Prizes, theoretical models, or technological achievements. Rather, it is found in the ways his work reshaped our understanding of nature and compelled society to grapple with the moral dimensions of human ingenuity. As we examine his place in science, energy, and ethics, Fermi emerges not only as an architect of the atomic age, but as a lasting symbol of the responsibilities that come with discovery. Chapter 20, The Architect Remembered, Fermi's Place in History. Enrico Fermi occupies a singular place in the annals of scientific history, hailed not only for his intellect but for the indelible mark he left upon the world. Remembered as the architect of the atomic age, Fermi's presence looms large in the collective memory of both the scientific community and the broader public consciousness. Understanding how Fermi is remembered reveals the dual nature of his legacy, one of extraordinary advancement and sobering consequence. Fermi's recognition began within his lifetime, unusual for many scientists whose contributions are often lauded posthumously. His 1938 Nobel Prize in Physics, awarded for his demonstrations of new radioactive elements produced by neutron irradiation, and for the discovery of nuclear reactions brought about by slow neutrons, secured his reputation as a prodigious talent. This honor, bestowed during a period of political upheaval in Europe, prompted Fermi to emigrate from fascist Italy to the United States, a move that would have dramatic implications for his career and for world history. The transformation from a celebrated theorist and experimentalist in Italy to a foundational figure in American scientific research was swift and remarkable. In the United States, Fermi became a central architect of the nation's atomic program, which would alter global power structures for generations. His work at Columbia University and then the University of Chicago reflected both continuity with his European achievements and an embrace of the burgeoning multidisciplinary approach favored by American laboratories. Historians and physicists recall Fermi as a bridge between disparate scientific traditions. His rare blend of theoretical acumen and experimental skill earned him the admiration of his peers, who referred to him as the last man who knew everything, a nod to his breadth of expertise. At a time when physics was fragmenting into ever narrower specialties, Fermi's contributions laid the groundwork for not only nuclear physics, but also for fields as varied as particle physics, solid-state physics, and electronic engineering. Fermi's place in history is also cemented by the ethical debates his life provokes. His leadership in the first sustained nuclear chain reaction, a watershed moment in human history, represents the dawn of a new epoch, one characterized by both human progress and existential risk. Today, the image of Fermi presiding over CP1, the first nuclear pile, encapsulates both the promise of boundless energy and the threat of nuclear annihilation. Biographers, colleagues, and students remember Fermi as a paragon of integrity, humility, and intellectual generosity. Not only did he mentor a cohort of scientists who would themselves rise to prominence, but he also shaped the ethical contours of scientific inquiry. While he was, at times, criticized for his pragmatism and faith in the self-correcting nature of open science, Fermi understood that knowledge could not be constrained by artificial barriers, even as he recognized the necessity of ethical deliberation regarding its uses. The remembrance of Fermi's role in history is continually shaped by each new challenge presented by nuclear science and technology, as issues such as nuclear proliferation, energy policy, and the stewardship of scientific progress persist. Fermi's story remains a touchstone for reflection and debate. He is frequently invoked when grappling with questions about the limits of innovation, the responsibilities of scientists, and the societal impacts of discovery. In museum exhibits, scientific symposia, and history books, Fermi is depicted as both a man of his era and a figure of enduring relevance. The enduring metaphor of the architect crystallizes his ability to both construct new realms of understanding and to foresee the structures, both tangible and moral, that would arise from such foundations. Ultimately, Enrico Fermi's position in the panorama of history is secure, not only because of his technical genius, but also due to the richness and complexity of his legacy. He is remembered as a harbinger of possibility and caution, a builder of bridges between nations and disciplines, and a visionary whose intellectual inheritance guides the evolving dialogue between science and society. As the atomic age unfolds, the memory of Fermi continues to inspire admiration, debate, and a profound sense of responsibility.